on Mondays. There's not much time for the exam. We will do some reviewing on Friday, but if you're preparing over the break, let's see, where did our last exam leave off? This is exam 2 we're going on to now? Is that right? So it looks like our last exam, we did all of fields, right? Fields and forces. So we pick up with chapter 1.5. That's the one on gravitational fields, flux. Remember we did the flux of the cube and then use Gauss's law to figure out the amount of mass in the cube. You'll probably have one question about that on the free response. And then we move into chapter 2, and it's all chapter 2 basically. So we got electric potential energy, or you might see that in form of gravitational potential energy, which was also in that 1.5. But they work out exactly the same way. We have capacitors, capacitor circuits. You will have a capacitor circuit similar to the one that we worked last time. We might do another one today. I don't know, is that it? I think that's about it. Potential energy, yeah, and capacitors. I think that we'll probably move on to chapter 3, but let's not put chapter 3 on the exam because chapter 3 fits better with chapter 4. And I think we'll just, like if we move into chapter 3, but you won't see it on the exam. Let's see, let's look at some more of these. Maybe we'll do another example of capacitors, and then we need to finish up the concept test. Remember last time we looked at this circuit, and really the hard part was moving from here to here. And once you get this, it becomes fairly straightforward. Well, not straightforward, but it becomes simpler than looking at this circuit and trying to figure out what all the heck is going on. But once you figure out that this goes here, that this is the same circuit, then it becomes a little bit easier, not a whole lot easier. You need to find the equivalent capacitance, like we've been doing, where you take the smallest part that is either series or parallel and combine those. And I like to draw my circuit as I move along, as I find the equivalent capacitance, moving from here to here. Let's go to the back of the book, and we'll do one more example that's like this. But I really encourage you to pick out some others, either in the homework or in the old test, because you'll certainly have a capacitor problem that is something like these. Let's see here. Let's try this one. So I'll give y'all a moment to, you might want to just sort of rewrite this circuit in a more regular fashion, or if you're able to look at it and just tell what's going on, that's great too. Remember, you start here and you move around and you begin to look for junctions. And so, like for example, here I have a junction, but notice that I have 3 branches that come after that junction. So that I know that I'm opening up a parallel branch that has 3 parts in it. And then I go through those, and then I come to this little part right here. I need to figure out what's happening there. So go ahead, I'll give you a minute to redraw that circuit. And your first step will be to find the equivalent capacitance. This one doesn't work out evenly, but that's okay. Well, yes, it's good practice. I'm going to start redrawing this. I'm going to draw it with the battery on the bottom. I just like doing that. Okay, so right here, this whole branch is sort of by itself because these all come back together. See, notice there are no elements, no electrical devices here. I can just sort of bring this all down to a point right here and then have it come out as a single wire. So those first four capacitors look like that. And then I open up another branch right here that only has two branches of a 4 and a 4 and a 2 and a 2. Or excuse me, a 4 and a 4 and a 2. And then it all goes back to the battery. All right, now I want to find my equivalent capacitance. There are a couple parts here that I need to start with. Here, a 3 and a 6, and here, a 4 and a 4 in series. Now both of those have a capacitance equivalent to what? You know? It's 2, right? 1 over a quarter plus a quarter is 2. 1 over a third plus a 6 is 2. So let's go ahead and redraw that again. So you may or may not need to draw all these, but I find it helpful. All right, so now I have 3, 2, and 6. And I have 2 and 2. And now I have 3 that are in parallel and 2 that are in parallel, so I find those. It's going to be 11 and 4. Now, on the test, I'll try to give you one where the numbers work out evenly, but you might have parts of your circuit where they don't. And so this is one of those where it just doesn't work out evenly. So we need to go through sort of the more arduous task of finding the equivalent capacitance, find the charge on that equivalent capacitance, and then we can find the voltage on each of the capacitors. So first we'll find the equivalent. That's 1 over 11 plus 1 over 4. Somebody could double check me out. I'll try to get it right, but I don't always. I get 2.9 microfarads. Anybody confirm that? You got that? Okay, awesome. Make sure that you can do those fractions. You got to watch your order of operations in your calculator. So make sure that you can do those. You're aware of how to do it. All right. So if I have 2.9 microfarads, that's my overall equivalent. I asked for that in this problem. It was so this is 2.9 microfarads. Then I need to find my equivalent charge, which is going to be C times V. That's going to be 2.9 times 12. It's about 36 or so. 34, what is so-called 35 microcoulombs. That means that I have 35 microcoulombs here and 35 microcoulombs here. All right. Now, anytime I get two values, I can find the third value. So if I want to know the potential, V is equal to Q divided by C. So that's 35 over 11. Just 3.2 volts. And then I can just go over here and say that this is 12 minus 3.2, which is 8.8. Now you might get slightly different answers if you do 35 over 4. What do you get if you do 35 over 4? You get you get 8.75. So you should have some consistency here that I can take the sum of these numbers and they equal 12, and then those numbers I can also find by doing the Q over C. All right, so that's 8.8 and 3.2 volts. Now we can start to fill in some of our voltages. I know that I got 3.2 volts here, 3.2 volts here, because those are in parallel. I also know, by the way, that I have 3.2 volts shared between those two capacitors. And over here I have 8.8 volts. And I'm going to write this in. I have 4.4 volts here and 4.4 volts there. The reason I was able to do that is because these are two identical capacitors and they split it up evenly. Capacitors in series split voltages. Capacitors in parallel and resistors, we'll see, share voltages. They share the same voltage. Okay? How y'all sit with this? You okay so far? Listen, it's easy when somebody's doing it in front of you, but you really need to sit down with a blank sheet of paper in front of you with a circuit and try it on your own, because that's really when you tell if you know it or not. But you're going to follow this same procedure. Now, one last thing. We basically answered every question now because we have the voltages for all of them. Now I need to know what is this voltage. You follow the same procedure. You say that the equivalent, I'm going to use it for charges, red. The charge on this one is equal to 3.2 times 6. Not 6, I'm sorry, times 2. So I got 6.4 microcoulombs on that capacitor. That means I have 6.4 here and 6.4 here. All right? You with me? Because capacitors in series have the same charge. Once I find the charge on the equivalent, I can find the charge on the individual capacitors because they're the same. And then the voltage for this is Q divided by C, 6.4 divided by 3 is 2.1 volts. And then the voltage on this is going to be 3.2 minus 2.1, which is what, 1.1 volts. So that's every answer. We have the voltages anyway. Let's just fill these in. So for C1, we had 3.2 volts. That is this one. C2 and C3, I had 2.1 and 1.1 volts. For C4, that's this one. I have 3.2 volts. C5 and C6, I had 4.4. And then C7, I had 8.8 volts. Now you can go in and figure out what is the charge. You just say Q1 equals C1 V1, which is going to be 3 times 3.2, which is 9.6 microcoulombs. And you go through and do the rest of them. Now, if you make a mistake on the voltage, and it's a reasonable mistake, I don't just make up numbers, but if you make a mistake on the voltage that carries through the rest of the problem, I won't count off every piece of it. If you just make one mistake, that propagates through. And then likewise, if you make a mistake here, but then you miscalculate Q, then I won't count off your Q. I'll give you partial credit. I'll give Andrew partial credit. But you do need to know how to do these circuits and how to analyze them. I find that students stumble. It's sort of a spatial thing that you need to learn how to spatially see the circuit and sort of deconstruct it in your mind. But that's something that comes with practice. That is something that you can do. You just need to practice. Nobody can do it before they didn't do it before. But now that with practice you can learn to do it. Okay? It'll help you when we go into resistor circuits. It helps you in chemistry too, because it's good in chemistry to be able to imagine how things are arranged in your mind. Okay? Circuits are kind of fun, right? Even at 7:30 in the morning. They're kind of fun. A little bit? All right. Let's, you will have that for sure on the test. Let's go back. One more little topic on this chapter. It has to do with energy. The purpose of capacitors is to store energy. That's sort of a primary purpose. Actually, capacitors will serve a sort of a different purpose as well we'll see as we move into RC circuits, where we join a resistor and a capacitor together, and you'll do that in PChem too. And then we go on into inductors and look at how inductors, how they interact with capacitors, and then we look at how inductors, resistors, and capacitors all interact. So we'll see that capacitors actually help us to have a time variable circuit, that they can give us particular frequencies with a circuit when we get into alternating current. But for now, we're just concerned with capacitors because they store energy, and that can be a useful thing. Let me show you a little video, actually. This is some guy, I don't know where he lives, probably up in New England, where everybody's crazy up in New England, right? And we can calculate this energy by this equation. The energy is equal to 1/2 CV squared. And so, for example, if we have a capacitor, say this capacitor, and we want to know the energy on it, we would say 1/2 CV squared, which is 1/2 of the capacitance, 10 microfarads, times the voltage, 2 volts, squared, so that's 5 times 4, that's 20 microjoules. And that's really all there is to it. We'll see energy again later when we get into these other kind of funky circuits where we have different things coming in. But I just want to introduce it now. Let's try this little quick test. Oh, let me pull the clicker up. Okay, sorry about that. What is the energy? How much energy does this capacitor hold? All right, let's just do about 10 more seconds. Still missing a few people, but we'll stop at, say, 53. 53. I think that's everybody. All right, good. A is right. Let's see, somebody put C. Be careful, okay, because watch your units. The SI unit for energy is the joule, and that's, you put 15, but the answer is actually 1.5 times 10 to the minus 4, because our energy is 1/2 of 3 microfarads times 10 squared, and so that works out to be 50 times 3, 150 microjoules. But that's equal to 150 times 10 to the minus 6 joules, which is equivalent to this 1.5 times 10 to the minus 4. All right, I move my decimal place over, and it becomes 1.5 times 10 to the minus 4. I have to add 2 to my, my exponent. Okay, so just be careful with your units, check the units. You're probably not going to encounter, you might have a multiple choice question, but usually on the free response, I allow you whatever units you choose. All right, that's it for that chapter. Let's wrap up the concept test. We had, I think, a bit left there. Can somebody tell me where we left off on this? Hmm. 2.7. Thank you, Nicole. This one? All right. So remember, well, this has to do with work. Remember, work is F dot P, our force dotted with our displacement. So which of these requires the most work to move a positive charge? Is it to move it from point P to 1, 2, 3, or 4? Or they all require the same which requires the most? All right, let's stop at 55. 55. Okay, good. A is right. Yeah, A is right. I have this positive charge sitting in this electric field, and so the electric field is pushing it in that direction. So I'm going to have to push my charge in this direction. So if I have my force in that direction and my displacement is also in that direction, then I'm doing positive work to move this charge in this direction. On the other hand, if I have my charge here and it's going in that direction, I actually have to hold it back, right? Because the electric field is already pushing in that direction, and I just sort of have to hold it while it moves in that direction. So in that case, for direction 4, my force is in this direction, and my displacement is in that direction. Right? Remember, that gives us a negative work. These others have varying other degrees of work, but well, there's another question about it. But A is the right answer. That moving in the direction towards 1 gives the most work. Which requires 0 work? We've already said that 1 and 4, 1 is positive, 4 is negative work. Which of these requires 0 work? Remember your dot product, that your work is F dot D. And what does that mean for a dot product regarding the vectors? All right, let's stop at 35. 35. Okay, good. C is right. Because remember, our work is F dot D. In this case, my force would be in this direction, and my displacement would be in this direction. Actually, my force, I'm sorry, wouldn't be in that direction. It would be in this direction, because I sort of have to hold it back from going forward. But the point is they're perpendicular, and the dot product there is 0. What y'all do on that? That's close enough. Listen, I go home for lunch today. My wife, we don't get to go home for lunch just a couple days a week, but I go home for lunch. And you know what the best thing about going home for lunch is? I mean, get away from here, it's sort of quiet, you get to be away. But when I go home for lunch, I get to have a Coke with my lunch. And I like those little Cokes. You ever seen them? Like, they're the little cans of Coke. They're like 8 ounces. Love those things. Do you know where they make them? Minnesota. See, I didn't think that was a joke, right? You just thought I was telling you a story. Am I right? All right. We have a few capacitor questions. I think we had a very similar one to this in the chapter. All right, let's stop at 50, please. 50. Just guess if you're not sure. Okay, B is right. So you have two identical capacitors. Q is equal to CV. The one with the bigger voltage will have the bigger amount of charge. So one capacitor is hooked up to 5 volts, one is hooked up to 10 volts, but otherwise the capacitors are identical. They have the same capacity to store charge, and so the one that stores the most charge is the one with the most voltage. So B is right. A lot of y'all put C, huh? What's that? They have the same capacitance?
Yeah.
Yeah. So they do have the same capacitance. So it's sort of like a bucket. Like you can think of a capacitor as a bucket. And so you have 2 5-gallon buckets, right? Now, you don't have to have 5 gallons of water in the bucket. You can have 3 gallons of water in the bucket. So they have the same capacity to store water, but they don't necessarily have to store the full amount of water. So you can think of capacitors sort of in that way, as a bucket to store charges. And if you have a water hose that puts out more water, then your bucket will hold more water. Likewise, if you have a battery that puts out more charges, has more energy given to the charges, then it'll get more charges into the bucket. All right? Y'all clear with me on this? Yeah? All right. We have a couple more questions that are similar. What must be done to a capacitor in order to increase the amount of charge it can hold? So you have it hooked up to a battery, say 10 volts or whatever. What can you do to the capacitor to increase the amount of charge it can hold? You increase the area of the plates, make the plates closer together, make the plates smaller, or some combination of those. All right, let's stop at 47. Was that D or is that E? D, A or B? Right, so remember, just want to go back to our equation for capacitance. Kappa, epsilon naught, A over D. Remember kappa, that's that dielectric constant, that wax paper you put in between the two metal plates. If I increase this, that increases the capacitance. Likewise, if I decrease this, that also increases the capacitance because I have this, inverse relationship between C and D. If I increase the area, it increases the capacitance. If I decrease the separation, it also increases the capacitance. So that would be like a variable capacitor. Like y'all dealt with variable resistors, I think, in the lab, or many of you have the little decade boxes. This is like a variable capacitor. All right, now let's say that we hook up our capacitor to a 400 volt power supply. That means that the voltage is going to be constant on this capacitor. It'll always be 400 volts. But then you do something to the capacitor. You double the plate spacing. So you take your plates and you move them twice as far away. What's going to happen to either the voltage or the charge, or both? Voltage is constant, but I increase the separation. I double it, in fact. What happens to the voltage and or the charge? All right, doing pretty well. A few of you don't have the right answer, but many of you do. Feel free to ask your neighbor what they put. All right, I'm going to stop here in just a few seconds. I'll stop at 1:13, say. Okay, yeah, so it's C. Now, the voltage doesn't change. I said that earlier, but because it's hooked up to the 400 volt power supply, it doesn't change. It stays 400 volts. So that's sort of key that the voltage remains constant. But then C is the right answer, because if I think about my capacitance, I change the size of that bucket, and so it changes how much it can hold. So my plate spacing goes up. That means my capacitance goes down. And remember, Q is equal to CV. If this is constant and this decreases, that means this decreases. So the charge will decrease in this case. You'll certainly have one or two questions about this in the multiple choice part of the exam, where I ask you about how the voltage or the charge of a capacitor changes when you change its qualities. Oh, how would you decrease the charge, or how would you increase the charge? What could you do to the capacitor to increase the charge? You can move them closer together. What else could you do? Right, you make them bigger. That makes that bucket bigger. Moving them closer together sort of allows you to use the energy of the battery more effectively. Put more charges on there. Okay, so now you charge a capacitor and you take it out of the circuit. So now your capacitor has so much charge on it. And then you double the plate spacing, move those plates farther apart. What's going to happen to the voltage? What will be the new voltage? I'm going to write our equations up here just to remind you. All right, y'all are split pretty evenly between B and D. And I think you're thinking right, because you know there are no quadratic relationships here. So it's either a direct or an inverse linear relationship. And if I'm doubling then the plate spacing, that means I'm either doubling the voltage or having the voltage. And that's good. That's a good way to think about the problem. It is either B or D. All right, let's stop at 120. 120. All right, let's see here. So if I double my plate spacing, I double D, I have my capacitance. If I have my capacitance, remember the charge is constant. When I pull it out of that circuit, it has whatever charge it has. So if I have that, I double my voltage. And so that gives me, it was 400, it's going to be 800. Very good. It's a nice way to have a variable voltage supply without actually having a voltage, that you can change the properties of your capacitor. And you might say, well, gosh, it's kind of hard to change the size of those plates. But it's not hard to add in another capacitor, like have a circuit where you have a switch that brings in another capacitor in some other way, either in parallel or series, which would change the capacitance and then change the voltage that you have across those capacitors. All right, what is the equivalent capacitance of this circuit? They're all identical. C, C, and C. What's the equivalent? All right, let's stop at 55. 55? Just guess if you're not sure. Ask your neighbor if you like, but there's sort of a range of answers we have out there. I'll stop at 1 minute, actually. 1 minute. All right, you should be able to do these, okay? The answer is A, but only 7 of you got that. But you should be able to do questions like this. You'll see them on the multiple choice part. And then, of course, it's important for your free response, too, because you need to be able to do these things. First, I start with these two. Let me redraw it just a little bit, because the little elbow there might throw you off a little bit. These two circuits are the same. Oh, goodness. these two circuits are the same. I have C, C, and C. I find this, that's 1 over C plus 1 over C. That's 1 over 2 over C, which is C divided by 2. So two capacitors in series are half their original capacitance. So I have C over 2 combined with C, so I get C plus C over 2, and that's going to be 3/2 C. So A is the right answer there. Be able to look at things like this and determine the equivalent capacitance. All right, same circuit. There's some numbers here. How does the voltage across the first capacitor, C1, compare to the voltage across this capacitor? In fact, you should be able to tell me what are the voltages on all those capacitors without any calculations. Remember, folks, capacitors in parallel have the same voltage. So whatever voltage I have here, I also have in this branch of the circuit. Capacitors in series split the voltage. Capacitors in parallel share the same voltage. Capacitors in series split up the voltage amongst themselves. So how does the voltage of V1 compare to V2? I'm going to stop here in just a few seconds. Stop at 110. Okay, good. B is right. I have, in fact, 10 volts here and 5 volts here and here, because those two in series, they share 10 volts because they're in parallel with the other one, but they split it up amongst themselves. And because they're identical, they split it identically. All right? Ever tell you, I told you I used to work at a bar, like at a restaurant as a bartender. And one night, I was there, it was late. I mean, we had a football game, we played in Tuscaloosa, Alabama, and it was just crazy on there. So I went to Starkville, right, just to be safe. And this mushroom walks into the Harvey's. Mushroom. The guy dressed up in a mushroom suit. I'm like, dude, we're closed. You can't come in. We don't even allow mushrooms at this establishment. And he said, hey, I'm a fun guy. That didn't really happen. I really didn't work there, but he didn't. That guy didn't come in. Neither a mushroom nor a guy in a mushroom suit. Okay, how does the charge on the first capacitor compare with the charge on the second capacitor? All right, folks, listen. So we've already said that the voltage here is what? Same circuit. This voltage is what? 10 volts. These two have 10 volts between them, but they split it up. So this one has 5 and this one has 5. So I want to know, how does this charge compare to this charge? Is it equal? Is it bigger? Or is it smaller? It's not 0. But is it equal, bigger, or smaller, the charge on C1, which has 10 volts? All right, that's a lot better. I'm going to stop at 1 minute. 1 minute. All right, good. B is right. In fact, it has 10 microcoulombs, and the other one has 5 microcoulombs. All right, you'll need a little work on the capacitors. All right, so you need to practice going over the properties of capacitors, and then also practicing the circuits, just in general as a class. So I know y'all want to relax and, do whatever it is that you do on Mardi Gras, but try to set aside a few hours to go through the homework for this chapter. And then also, it's been, some time since we did those previous chapters, so our exam's not that far away. And it's kind of a big exam. This is one of the more difficult exams. So please, I don't want to scare you, but I want to scare you a little bit. Please spend appropriate time on it. But we'll stop there. I'll let you out a little early. So have a good day, okay? Have a good break. Do good. Relax and stuff on your break too. Dustin? computer book.